So just as a note, so first off, can everybody hear me? Just want to make sure. Everybody in the back can hear me? Fine? Because I can speak quite louder. Let's see. So first order of business, I record all my lectures, which you'll be very happy about, I'm sure. But just be aware of that, and also because Pennsylvania is a two-party consent recording state, I do actually have to make you aware of the fact that I'm recording. So it is in the syllabus, so but you know. So okay. So let's go ahead and head over to your course, and then I'm briefly going to go over the syllabus, and then I'm going to talk about the bit of computer science history. By the way, did you know you can make animated GIFs be the icon for your Canvas page? I found that out last year, and I've had fun with it ever since. So, all right. So this is 1051. It is intended for students who have basically not had the chance to get any AP credit for computer science, who haven't taken any computer science, or they've taken some programming, but they don't feel like they're ready for to basically skip any courses at the college level. Basically, if this is your first time programming or close to it, you're in the right place, right? If, on the other hand, you've basically done a lot of programming and know what a linked list is and binary search trees are, and if you've got recursion, then if you know how to do recursion, this is going to be a cakewalk. So, but otherwise. But the intention here is that if you don't know anything, that's perfectly fine. You're in the right place, and this course will be catered towards you. So here's the syllabus. Notice that basically I've got two big bullet points at the very first page emphasized here. So the first is a way to instantly fail the class. Okay? So yeah, I got everybody's attention there. So uttering some variation of the phrase, "I did not know we needed to demo our assignments to receive credit," after the first exam, we'll receive an instant F in the course. Okay? So saying "I did not know we needed to demo our assignments" after we have our first exam will result in an instant 0. For failure to read your directions, because failure to read directions in computer science has lethal consequences. And so I'm not going to pass you. The other important point that's less morbid is that you need to sign up for your you'll want to sign up for your textbook at Runestone Academy using the course name CIS 1050. You will not have to pay a dime for this. I have enrolled in the the textbook affordability project that I saw a flyer for it, and I thought that's a great idea because I hate paying for textbooks. You probably hate paying for textbooks. So we're using a free online textbook. I'm going to be following it fairly closely. There's only one chapter. There's only one section of stuff I plan that's not going to be in that textbook, and that's going to be coming from another textbook that's under Common Course stuff. So you'll be able to get access to that freely. The only disadvantage is that if you need a printed copy, you're going to probably have to print it yourself, which is a bit of a pain. But otherwise, you can read it on your phone, on your computer, anywhere. Just sign up for when you enroll, use the course name CIS 1051. All right. So course details. So the idea here is to give non-programmers a sufficient amount of programming experience to basically apply. So basically, I kind of teach this course basically with a couple of different motivations. First motivation is that you're never going to take another programming course again after this because you're not in a computer science major or you're not going for a minor. You're just here because you want to learn how to program a little bit, right? And I'm sure that fits the definition of some people, right? You might be a senior. This is your last semester. You might be dipping your toes wet to see if this is the right thing for you. So I will not make an assumption that basically you're planning on going on to another course, right? This is just simply the assumption that you learn useful knowledge here. This isn't, oh, it will all become useful later. This is, no, the stuff you learn in this course, by the time you finish this course, you'll be able to use it regardless of of whatever course you're in, right? You can use it whatever. You can use it in the future. If you're in the CIS program, or if you're going for a minor, then you're going to learn that plus a bunch of other concepts that are going to be useful for 1068 and 2168, which are the future courses that we do here. It's a 4-hour credit course, which means that if you do if you follow the rule, basically 1 credit hour is 2 to 3 hours, 2 to 3 hours outside of class, and it is 8 to 12 hours of work each week outside of lecture that you'd be expected to do in either studying or in the homework. And that's just because programming problems just tend to basically, they tend to be annoying. In the sense that basically you're your own worst enemy, you're going to read something and you're going to read it multiple times, and then you're going to realize, wait, what I just read isn't actually what I wrote down, and then you're going to have to fix it. And so congratulations. I have to put this in the syllabus. I don't know why, because you find out where your course is not by the syllabus, but from the fact that you enrolled online and then it has that location. That's how I find out. So here's your labs and your lab times. This kind of exploded. We went from having 5 sections to 6 sections, so it's a lot of students. I have taught this in a large section course. I also taught this course in our satellite campus in Japan last year, but that was with 8 students, and that was a lot. Let's just say that it's a lot cozier when you've got only 8 students to deal with. So your prerequisites, you have to have a C in some math course. I think that's like college algebra or something. I don't know, or pre-calc. I'm not sure. Point is that there's some basic mathematical assumptions that are in there. Basically, we don't want you to have a panic attack whenever we say the word variable or function. So that's about it. So you're expected to know how to use a computer. So a laptop is strongly recommended, especially since we're going to be using an online textbook, although you can use your phone for that. If you don't have a laptop and you can't afford one, please see me. You might just simply be over budgeting for it. You can get by with $200 to $400 depending on what kind of workflow you're looking for. Like if you use an online code editor, which there's a number of them, including our textbook, you can get away with a netbook, right? And that can be pretty cheap, right? So you can do pretty much everything in the browser for a lot of the stuff. That will get you at least through this semester or a couple semesters. So resources and textbooks. So the most important resources for the class, such as the recordings for the class and the code. And right now I have last semester's code and last semester's lectures up there, and I might keep them up there. You can click on here and click on lectures, click on class code, right? And it will have, here's the playlist from last semester. I'll be creating a new playlist for this semester. And then if we go over here to class code, this will have a link to GitHub, which is a website that's very popular for using to store code online. And all of our code will be located in this ITP folder, which stands for Intro to Python. So you'll find that. So basically, I try to make all the stuff I do accessible, and I record my lectures for a couple reasons, right? If you're sick, I don't want you to come in here and get me sick or my kid sick. I've got a kid at home, and if he gets sick, it's, he's a 2-year-old, so there's snot everywhere because he hasn't mastered the whole concept of you need to blow your nose into a tissue thing. So, that's just the way it works. Plus, your fellow students are going to probably get something from you. So if you're sick and you need to miss class, just let me know. I'll make you make up whatever you missed and watch the recording. Same with an exam. If you're sick, just let me know if you have to miss an exam because you're sick, and we'll arrange a makeup. I try to be pretty lenient about this because I haven't seen too many students try to abuse this. All right, but the lectures are there for you to review. They're there for if you need to miss a lecture for some reason. They're there if you need to double check your notes to make sure there's what's being compared to what I said. So this is the textbook that we've got, The Foundations of Python Programming. It's at Runestone Academy. You can click this link. This is it. The way you get access to the course is hit sign up over here, enter whatever username you want, put in your actual first name and last name so I can know, so that when it comes time to export this kind of data, I know who you actually are. Use your email, whatever email you want, create a password, and then over here you just type in CIS 1051, and that will get you to our online textbook. Our online textbook was designed for a flipped classroom. We're not really doing a flipped classroom. This is mainly just so you have something to read and for something to basically for us to follow along. It's Foundations of Python Programming. And what's really cool about this is that what we'll see is that basically we can, is that you'll see that we can run the code in the browser. Let's see, is that not running? Did I just choose the one that's, oh, did I just choose the one that's going to have issues running? Yeah, I did just choose the one that's going to have issues running. Great. So that was exciting. So, or maybe it's just an issue with my browser. Okay. Let's see. Right. So if I hit run, there we go. It will execute the code in the browser, which is pretty nice. Right. So I'm expecting you to install Python on your own computer, but in a pinch, you can just hop on any computer and use the browser in here, and you can run the code segments, you can play with the code segments and experiment and do that kind of self-discovery that's supposed to be good for you guys. So, no, but actually experimenting and just playing around and messing around with something that catches your interest is the best way to learn something, especially in programming. There's also if you need additional resources on the material, I've listed 2 additional textbooks. Al Sweigart's Automate the Boring Stuff with Python, which is designed for people who are basically got a business degree and now they want to learn some programming, or people who have not learned some programming and now they're in a job and they need to automate something like doing something with Excel, and this teaches you how to write Python scripts that make your job a whole lot easier. We'll be using one chapter from there later on, but it's a very good book. I used it last semester. But it's not like the best academic book. The exercises, in my opinion, were lacking, but the content was good. They also, Think Python, How to Think a Computer Scientist. This book over here takes a lot of stuff from this one, but this one has also these 2 books do have a hard copy, and if you want one, they're available for $20, $30. And they cover basically the same, they're just covering a lot of the same stuff we'll cover, but in a different way. And also, Python has its own built-in tutorials, which you can find here. So my office is in Circ 349. I have a big chunk of office hours because I have a big chunk of students. So my office hours are 12 to 3 on Wednesday. That may not work for some of you. That's okay, because you can always arrange to meet with me. Right? You can send me an email saying, hey, can we meet after lecture? Or, hey, can we do this? Or can we meet like before noon on Tuesday or Thursday, or some other time during Wednesday? Sure, we'll work out a common time. If we can't both be on campus at the same time, I will do voice over the internet with you, or video over, I'll do video chat with you. And that typically works out fairly well because I can totally take control of a screen if you let me, and like I can, say, oh, this needs to be fixed. We have 5 TAs for this course. I do need to put in all their office hours. I'm just still collecting them. Notice that I have not listed which TA goes to which lab. That's because you can go and visit any TA listed here or ask any of them listed here. So they'll all have different office hours. Some of them will be during some different labs, but that's okay. You're, by the way, expected to go to your lab. Your specific lab. Executive summary of the rest of the stuff. Don't cheat. We're going to expect a new lab and homework and quiz each week. We're going to record the lectures. Turn in your work on time. There's a late penalty, but it's not that bad. So it's okay to turn your stuff in late, but if you don't want a penalty, turn it on time. Don't ignore any errors as you code, because as you code, it's best not to just go backwards and try to fix it later. You want to fix it now. You need to show me your work to actually get a grade. And I literally mean show me your work, or show your TA the work by literally coming up to them and showing them what you did. Exams, though, are the most of your grade. And most importantly, never be afraid to ask a question or ask for help, because I guarantee you that 5-10 other people will have the same question. This is an intro course. I'm not going to think you're stupid. I'm just going to think I failed to explain something, or I didn't explain something yet. So it's perfectly valid to have a question, right? Especially in an intro course. I do expect you to attend the lectures, because there's a huge correlation between attendance and performance, and that's also going to be where our in-class quizzes are. They're not particularly strenuous or onerous. They're going to be mainly done on Canvas. So yeah. Again, illness, just Oh, yeah. Why else to attend lecture? I'm prone to mentioning what will and won't be on the test, up to and including some exact questions that will be on the exam. So, show up. Academic honesty. Don't plagiarize. Right? This is a big one for computer science. So let me just be frank. Pattern recognition, which is what's used to detect plagiarism. That's a subdomain of computer science. I've heard that computer science has a higher plagiarism rate than other disciplines. I believe this is false. I believe that basically computer science is just simply better at than everybody else at detecting them. So don't plagiarize. Now, when in doubt, provide a citation. Working with others and creating your own unique solutions to not cheating. Saying that I collaborated with this person, right, on your or Susan helped me with this write this function, right, or something like that. That's not cheating. Worst case scenario in that case, if you've cited the work, I can simply just tell you you have to redo it yourself, but it won't be it won't be plagiarism, right? Copying somebody else's work is cheating. Going online and looking up how to do it and copying and pasting it is cheating. Looking online and seeing that basically there's a fun function that I haven't taught you yet and totally solves that problem that will take 10 lines to do in 1 line of code, not cheating. That's research, right? Finding out that there's something built into the Python language. When in doubt, ask. All right. I don't know why I'm telling you to contact the person at TUJ because that's when I last revised that one. Anyway, if you have to have any kind of accommodation in class, extra time, and a note taker, anything, or something similar, any kind of accessibility needs, register with DRS and let me know. Again, I'm recording my lectures. If you're going to be recording your lectures, please tell me. One of the things is generally I will not be able to hear what students say. So if you're worried about your voice showing up, don't worry about that. It's not going to show up. I'm going to do my best to repeat questions. But anyway, if you make your own recording, which you probably won't need to, just got to let me know. So grading, right? So as it follows, this is the breakdown for the grading in general. A's are guaranteed at 90% or higher, B's at 90% or higher, but there's a curve involved. Last spring it was like an 87, no, I think it was like an 88 was a minus. 88 and above was guaranteed to be an A minus. If you got a 90 and above, it was guaranteed to be an A. So I use the minuses to kind of curve people up into the next letter grade category. So like a B was a 77 and above in this course. So generally, though, you won't pass with below a 70. It's very rare that happens. What we see is a bimodal distribution in this course. Basically, you get a cluster of students who get it and this cluster of students who are really struggling. So the DWF rate, so D's, fails, and withdraws, is for similar courses and previous semesters. I'm going to be frank, it's around 30% for large classes. This is because people just go, you know what? Not what I want to do. Some people go like, you know what? Alcohol sounds much better than going to class, and they, don't plan accordingly. Or it can be like my first semester, where basically you weren't challenged in high school at all, and now you get into college, and because you weren't challenged in high school at all, you've got no good study habits. And then you think, oh yeah, 4 hours before the deadline, I can sure get that done. And then you realize, I guess I can't. So totally happened to me. I had C's and B's my very first semester of college. It wasn't until my junior year that I started getting A's. But part of it's because, a lot of freshmen and underclassmen in this class. So that said, I rarely give out Fs. To get an F, you have to not try, essentially. You have to not be doing the quizzes, you have to not turn in any of the homeworks, and you got to completely and utterly fail on the exams. If you, however, completely and utterly fail on the exams but have been trying, that's a D in my book. Okay? So the difference between an F or D is, have you been putting in the effort in this class? Non-numerical difference. That's right. So, and part of that is because that Fs impose all these weird things with financial aid office, and it's just a pain in the butt to deal with. So Ds are much easier, and you can't go on next anyway. So, all right. So there's going to be extra credit opportunities available on exams and on assignments. I don't give out extra assignments or tests. You might have like an extra credit assignment, but like to you or specifically, I'm not going to say, well, can you give me an extra assignment to do or an extra exam to do? I'm not going to give you that. But I will drop like a lab. I think I dropped like 2 labs last semester. So, so 2 weeks of the worth of work we were able to drop. And some students were like, well, I did everything, so I don't have to do anything this last week. So the final grade is basically the average of all these things in each category. So all your assignments are averaged and are 25% of your grade. So your exercises, which are problems I'll assign in the textbook, are basically 5% of your grade. And basically I'll just be checking, have you done this? This is kind of this and your quizzes are basically your participation grade. Basically in-class participation, out-of-class studying, so to speak. These are going to be basic stuff with basically unlimited number of attempts on the exercises, and for the quizzes, it's just going to be like, we'll be giving them in class, and there's a lot of freebie points in there. So, like multiple choice questions with one answer, because that's also a way I count participation. Your exams, so the regular midterms, the 2 of them are combined right now at 35% of the grade with so if you do the math, that's like 17% for each of those exams, and then your final exam's worth 30%. That's a lot. But programming courses are just, they're just a heavy amount of, they're just typically online. Yes?
This is 16.
Yes, Python.
Okay.
Yep.
Sorry.
No worries. Okay. So, all right, your program actually has to be able to run when in order to demo. Okay, last thing, important thing here, right? Submit a Python code, right? Don't submit a .txt, .doc, or .rtf. So how do you turn in your assignments, right? There's 100 and like, I don't know, there's 6 sections, 30 people per section or something like that. So 6 times 30, do the math, it's 180 people. That's a lot of grading to do. I hate grading. Actually, it's not so bad for Python. In Java, it's worse because there's all these folder issues and putting things in packages, and then everybody puts everything into a different package, and so you have to move folders around, and it's awful, just awful. So anyway, much easier for Python. Anyway, so I had this brilliant idea early on of like, well, why should I download it? I should make the students do that. So that's exactly what I'm doing. So anyway, to get your grade, it's a 2-part process. The first is you have to submit the grade it online to Canvas. This just simply puts in a paper trail for us, right? Saying, yeah, you submitted it at this time. It's not late, or it's 2 days late, not 5 days late, right? Or in case our Wi-Fi messes up and I can't enter the grade, at least we've got a paper trail that you did turn it in at this time. Okay, so it's just basically saying this is just basically being able to cover your butt on that one. The second point is that you have to demo it to me or a TA. Demoing your work involves showing your program works, explaining I'll ask you questions about it, you'll answer my questions, you'll explain what your source code is doing, right? But basically showing that you understand what you wrote. You didn't just randomly copy it from a friend. Demoing can be done before class, during some classes, if we're just doing in-class exercises, after class, if I've got time, during office hours, or during lab. So during my office, the best times to do it are, by the way, during your lab period, and the labs is time specifically set aside for you to work on your homework, right, and get help on it. So that's what the lab period is. So you can demo your assignment in lab, or you can go to my office hours or any of the 5 TAs' office hours, right? There will be time for you to demo it. How long do you have to demo it? Well, I'll say basically a month after you turn it in. Please try to demo it by then, right? So you can turn it in and like demo it a week later. You can finish it at the end of the lab, and then you can come back to the next lab and demo what you did last week. Late policy, 5% per day. That's not 5 points per day. That's 5%. First day late, 95. Second day late, 90.25, and so on and so forth. I will typically what I'll do is that I will cap the losses at 50%. So at some point, right, so if for some reason you've decided to spend half the semester playing an MMORPG and then realize you're failing everything, and then you come in and try, and there's still a chance to redo all your work for half credit. Okay. Furthermore, I try to be fair about like say you've got a 5-part assignment and you're only able to do 4 parts. So let's say, and then the next day you're able to do that last part. So you're going to get 80 points for the 4 points you did, assuming they're all weighted equally. And then that last 20-point part, you turned in 1 day late. And so we applied the late penalty to only that section, not into the entire thing. So you're only losing 2 points there, as opposed to 5 points. So I try to be fair about it, right? Okay. Yeah, and I had this old clause about 10 days at most, but you know what? I found that just letting students get it in and saying I'm super lenient about it doesn't mean that I have many people who take advantage of it. Okay, so formal exams account for like over half your grade. They're going to be roughly around week 5, week 6, and week 10, week 11. If I have to move them, I will, but it will basically be based on where we are in the content. I found that it might also be possible that I add in a 3rd exam. I might change it around just simply because I found that I can go slower, and if I give more exams, that means each one has less of a weight, right? So I'll let you know. So the thing about exams is that I will let you know at least a week in advance that there's going to be an exam the next week, and you will be provided with a practice exam. And what I do for the practice exams is I make twice as many questions as I need. I give half to you as a practice exam, and I keep the other half as the actual exam. So it's a very fair representation of what's going to be on the exam. For your notes, you can bring in a single sheet of paper, either letter or A4 or some comparable equivalent of those formats. In other words, something that looks like a standard sheet of paper. You can use both sides, and you can put anything on it you want in any way you want. Okay. Disclaimer, I might change this. You've been warned. You, believe it or not, do have rights. Click. It's serious. Like, so for instance, how many of you know at what point are you allowed to ask a professor to give you a final on a different day? If you have more than 2 finals scheduled for the same day, it is written into this big document that you can, or into the student policies, that you can ask one of the professors to move. So if you have 3 finals on the same day, you don't have to take 3 finals on the same day. You're allowed to ask one of the professors to move, and if none of them are going to move, you then ask the dean to ask one of them to move. You do not take more than 2 exams on the same day. Or 2 finals, rather. So, finals, not exams. So, should probably apply for exams, but finals. So, surprising things you find out when you read those kind of documents. All right. So, with that being said, let's talk about programming. So, the history of programming is pretty old, and I'll start there because people are going to be coming in and out of this class through the next period. But programming, let's see, do I have that lecture stored somewhere on my computer? I better. Okay, so teaching ITP. Yeah, I've got it over here. So first thing we should ask ourselves is like, so you're enrolled in a course that's under computer and information sciences. So I guess the first thing we should ask ourselves and clarify here is what is computer science, because there's a misconception, a huge misconception, which is that computer science is synonymous with programming. Now, this is a programming course, but programming in itself is not computer science. Whereas these guys, who I presume are important, put it, our computer science is no more about computers than astronomy is about telescope. Biology about microscopes, chemistry about beakers and test tubes. Science is not about the tools, it's about how we use them and what we find out when we do. So calling it computer science is kind of a misnomer, because we use computers to do what we need, but it's not the study of computers, no more than astronomy's, the study of telescope, right? So it's not programming in and of itself, which is, and it's an understandable conception because most of the time when we're exposed to programming, that's typically with a programming language like Java or Python. And there's nothing wrong with that because I did that. It's not about learning formal languages or learning about programming languages. The computer science subdomain or the pieces of it, did exist, but long before the formal programming languages showed up. Programming is kind of like this subdomain. It's kind of used to be like a subdomain of linguistics and mathematics and engineering and a bit of maybe business thrown in there. And then it's like like the Balkans, basically different pieces of countries all mixed together, and nobody's very happy about the way that has ended up. So so there is just so that's why you get things like like you get very interesting subdomains like human-computer interaction. That's part of computer science. It's cross-domain with biology. Bioinformatics, cross-domain with biology. In other words, looking at different sequences of genes, needing to look and basically trying to analyze them using computers. A lot of cancer research goes on thanks to computer science. So, so it's not specifically about learning any specific degree. If you learning any specific language, you're going to, by the time you've learned 2, you're going to be able to pick up a 3rd or 4th or 5th one very, very easily within like a couple weeks, right? Once you learn 1, it's not so hard to pick up the 2nd, and then it becomes very easy to pick up the 3rd. We don't study how to use a specific piece of software in depth. Like there's no class you'll find here that's like how to use Microsoft Excel. So we can easily define what it isn't. So a lot of people argue about the definition. Like one textbook gave the simple definition, and that I like because it's a not wrong definition. Not wrong. Computer science is the study of algorithms. Specifically, what we're looking at is how we automate problem solving. That's what computer science is. How do we automate problem solving? What can be automated when you get right down to it? What can we solve automatically? Also goes into the question, and then we have other deeper questions like, can computers solve things that humans can't? Or can humans solve things computers can't? Right? Is a human being's brain just a sufficiently advanced computer? Right? So that's just very interesting. So that gets into philosophical stuff that I try to veer away from. But when we say that computer science is a study of algorithms, we mean that studying the behavior of algorithms to see, hey, is that algorithm correct? Algorithm, by the way, being a word I'm obviously going to have to define because I don't expect you to know it. Designing and building computer systems that can execute these algorithms that we create. Designing programming languages to be able to actually implement our algorithms. So we have this idea, we have a system, now we need a way to describe our idea to this system. And then identifying the important problems and now that I have an idea, a way to implement this idea, and a system that can execute my ideas, I got to actually see what things are there worth having ideas about, right? What can we solve? So what can we solve with computer science, right? As I mentioned, bioinformatics, biology, chemistry, medicine. Bioinformatics is pretty big right now. This is stuff like basically doing like string sequencing to see, doing cancer detection, design of new medicines such as HIV inhibitors, right? Prosthetics research, right? I mean, you get all these cool 3D printed stuff that don't really have any electronics in them, but you can get really interesting prosthetics that basically, right, will have small computers in them. We've seen experiments where people have had their eye replaced with a mechanical camera, right? It's pretty cool stuff. Physics and astronomy, right? So getting into quantum computing, which is not something I'm really comfortable with. But basically supernova detection. So basically looking at the night sky and seeing stars exploding. Very little of that is actually done by humans anymore. It's all the person who gets to say I saw it first is generally the people who have the computers who are analyzing the night sky. There's tons of astronomy data coming in. So there's this Large Synoptic Survey Telescope, probably is already launched. 140 terabytes of data a day is expected. So figuring out how to process all that information, that's a lot. Engineering, business and economic. So we learn a lot about how to manage large teams in computer science. High-speed trading algorithms, that's where the big money's at, right? So let's see, like, oh gosh, micro crash. I think it was like in 2011 or 2012. Micro crash. Yeah, the 2010 flash crash, also known as the crash of 245. This is a picture of the stock market. Notice the scale is just in hours. This is the fault of computers doing high-speed trading without any human intervention. Led to some regulation on that because that was very scary to investors. But a lot of trading online between currencies and between things and stocks can be done by computers these days. You know, when you see like business channels go to the stock exchange floor, it's mainly just like a television set. Most of the trading doesn't go on there; it goes on computers. Okay, psychology. So human-computer interaction. That's where I got my start in undergraduate when I was doing my undergraduate studies, which was basically analyzing how can people use computers better. So coming up with like user interfaces and acoustical maps for blind users. How do you create educational software, right? How can you can we make our games into basically something that builds skills for children? Can we deliver educational content better to students? So let's go ahead and talk about what is an algorithm, since computer science is the study of algorithms. So the word algorithm comes from the Latinized name of Muhammad ibn Musa al-Khwarizmi. I think I pronounced it not too badly. But anyway, you know, and the scholars of the time, all speaking Latin, they just Latinized his name into Al-Ghamidi. Okay. Now you can blame him also for any pain you had in mathematics, because he wrote a book called The Concise Book of Calculation by Reduction, and that was his seminal work in 820. Old book. The first word of the title was Al-Jaber. By the way, he was Persian, I believe. So anyway, so Al-Jaber, it meant reduction, and so that's where we get the word algebra from. So you can blame him both for algorithm and algebra, or credit or blame him. So he also wrote this book on how to do these mathematical operations in this newfangled decimal system that came out of India, right? This new 10-digit number system this base 10 number system that had just come out of India. And so we talked about how to do operations in that, and then that was eventually translated into Latin, and then that's how that spread across Europe. So also base 10. So he helped basically spread the base 10 system as well. So we name algorithm after him, just not because of anything with computer science. It's just how it happened. So this Persian guy. Got an entire Wikipedia page about him if you're interested. So algorithm is a set of well-ordered, unambiguous operations that yield some result in a finite amount of time. That is the explicit definition. Honestly, I don't really expect you to memorize these things. If there's anything that's going to be on the exam from the first lecture, and there will be something on this exam from this lecture, it will be the question, what is computer science? And the answer that is not wrong is it's the study of algorithms. There you go. See, first day, that's 4 points on your first exam. All right. So an algorithm, so what does that mean? Well ordered. Well, that means that basically the steps of an algorithm basically have a specific step of things. So let's look at the recipe of baking cookies, for instance, right? You don't just simply take all the raw ingredients that you know, don't take the flour, you don't take the sugar, you don't take the eggs, and just toss them all individually into the oven and hope that everything works out. No, you have to mix them together first. The order in which you do stuff matters for baking cookies, right? Otherwise, you end up with a disgusting mess. Or you can just sell it for a high price and call it deconstructed. I don't know. So well-ordered means that basically there's a specific order in which we're going to do things. Unambiguous operations. So you're not going to say and just take a handful of chocolate chips and throw it into the batter. What's a handful? Like my handful is probably, I think my hands are fairly small, so I don't know. That's not equivalent to like one of my friends who has like giant and massive bear paws for hands, So, we like to say you want to add 200 grams of chips, of chocolate chips to the batter, right? Unambiguous mean, you don't want to say, and you don't want to then say in your next direction, put it into the oven. By it, do you mean the chocolate chips or the batter, right? No, you want to move the mixture into the oven, right, after spreading it out into cookies, right? So unambiguous. Computers are very good at making sure you're being unambiguous, though, but there's not going to be any room for misinterpreting what one line says or another, which yields some result. So it actually does something. Yields some result. It actually does something in a finite amount of time. So before the universe ends. In other words, it's just not going to run forever. It's going to run until it's done its job. All right. So some algorithms, most algorithms you've already been dealing with them for mathematics. So think about arithmetic algorithms, So for instance, doing addition and multiplication by hand, that is an algorithm. I will torture you guys by using the chalkboard for just a second. So, like, for instance, if we were going to add 195 to 276, there's an algorithm that we follow for adding these three-digit numbers, right? So what does our algorithm say? It says start with the ones place, add the two numbers in the one place together. We get 11. But instead of putting 11 down there, we put the 1 down and we move the 1 into the carries place. Then we repeat for the tens place, adding the carry and then the two tens digits together to get 17. And then we do that and we add the carries and these digits together to get 4 over here. Right? That's an algorithm. I followed an unambiguous number of steps to do that. And so the idea here, though, is that I'm lazy and I'd rather write a program to do that for me, right? So algorithms, once we turn them into a program, they become just something that can be automated again and again, right? We about like once every couple of years, we hear about a programmer getting fired because he doesn't actually do anything but browse Reddit all day because he had already written a bunch of programs to do his job for him. And this is kind of the ideal spot, though, basically getting most of your job done and automated and then not having to do anything about it. There was also this other case that I can't remember where a guy actually got sued and fired because what he ended up doing was rather than writing any programs to do it, he just paid a third of his salary to somebody in India or China to do all of his work for him. This was primarily bad because of intellectual property concerns, but he just by all appearances all the team members thought he was just exceedingly productive, but he spent most of his day just browsing the internet. So anyway, if you don't want to work, just pay a third of your salary to somebody in another country where the dollar stretches a bit more. All right, so that's pretty terrible. So this as so a bit more about the basis of computer science. So very, very brief history of basically computing stuff. So first thing that the first tool that we really had for doing algorithms was an abacus. It wasn't a computer storage, right? It's the thing that you had as a kid that went click, clack, with beads that you really never knew how to use. My son has one of those, and I still don't know how to use it. Right? It's not a computer, right? It was just simply a way of storing data, storing numbers. And so because it needed a human to do each of the steps. But around the 1600s to the 1800s, the idea of using gear machines that had gears that would turn and the position of the gears would give you an answer to do numerical computations, a bunch of scientists had that idea, right? I'm not going to say anybody had this idea first. It's really debatable. I'm sure somebody probably had the idea beforehand, just with not gears. I don't know. So Pascal, Leibniz, right? Two people that you can shake your hand angrily at him for physics. calculus, right? And Babbage, Charles Babbage, spent a lot of money on this stuff. Wanted to create a gear-based machine that could print the first that could print output on paper. Basically, get these two numbers to add stuff together, and then the output would appear on paper. Did a lot of scientific expeditions and stuff. And he met Ada Lovelace, as she was known before she got married, Ada Byron, daughter of the English poet Byron, who's credited with the Byronic hero. Now he and his wife were basically like the celebrities of the time. Like, they were huge, and their falling out was actually stuff that was basically like the talk for years. And when I say when I say for years, I mean like for years. They were still, after both of her parents were dead, they were people were still fighting about who was right and who was wrong years afterwards. But anyway, he was like a very adventurous, romantic kind of sort, in the sense that basically he went out and did, all these, he was just going around doing stuff and having fun. So, anyway, he had a very exciting life. Now, Ada's mother, on the other hand, saw this and saw, like, this guy's out of control. I don't want my daughter to be anything like him, and basically confined her to doing anything that was not artistic and just simply a bunch of numbers. So she became very studied in mathematics. Anyway, so she eventually came and met Babbage. So he had this analytical engine that he was designing but never produced. The analytical engine, the idea was you would take these paper cards that had holes punched in them, right? So that's actually something that eventually did get implemented, and then that would provide the instructions. And so Ada, what she did, she published a paper, and it showed that basically you could how you could program one of these cards to produce these Bernoulli numbers, which are a sequence of numbers you don't really need to know about. They're in statistics. You'll learn about them in statistics if you take it. It's not important, right? She just simply programmed this numerical sequence. You could say that this is basically because you had the system that was designed and a program, that you could consider her the first programmer. But her contribution was that she showed, well, actually, since it deals with numbers, we can encode basically things that are not numbers into numbers and then do computations on those. And thus we could maybe do operations on words and store words in there. This was about 100 years ahead of its time. Sadly, she died, I think, of a cancer at a young age, as all the Byrons were. The dying early was something that Byrons did, apparently. So, unfortunately, she never really got the chance to see, basically, her success, really. But, her contributions to computer science are pretty huge. The next big leap in computer science was the birth of modern cryptography, which was using machines to break German ciphers. This was the general effort was called Ultra, which was the cryptography effort to basically to break stuff during World War II in the German front. The Pacific Front was all the cryptography effort was called magic there. So if you had ultra magic classification, you were basically, the war was over for you. You did nothing but break codes all day in somewhere that you would not be killed. So now one of the ultra researchers was Alan Turing, and basically now you may have watched The Imitation Game about him, and I am very happy to say that actually he was much less curmudgeonly than the movie made him out to be. He was actually well liked and well respected by by many of his peers. So he got along a lot better than he did with other people in the movie. But anyway, but basically, they were able to crack the Enigma by building a machine to decrypt those words using, and there's a whole thing worth reading about of it. But in the end, Eisenhower basically said that Ultra and all of its efforts were decisive to an Allied victory and lowered and probably cut 2 years off the war. As far as the first, now Alan Turing was also died at an early age. He was gay at a time where it wasn't socially acceptable to be gay. He was basically arrested for the crime of being gay and was given the choice between chemical castration and imprisonment, and he chose chemical castration, which totally messed up his head, and then he eventually committed suicide. So the British government eventually apologized for that in the past decade, but still, it's somebody who was killed who died at a very early age, and unfortunately, wasn't able to basically fully see what basically his contributions to computer science did, because he was also known for the Turing machine, which is a mathematical definition or one of the two mathematical definitions that exist that define what a computer is and what operations you can do, and this kind of stuff, which we call automata theory, allows you to kind of prove what we can do with computers. Okay, so the first computer, it's contentious. There is no clear first computer. Some people will say ENIAC. This is Ada, by the way, a portrait of her. ENIAC, this big thing over here. So then there's a free museum that used to be the Chemical History Museum, by the way, in Philadelphia. You should go there. I don't know what its new name is now, but they have a nice display that shows basically, I think it goes from vacuum tubes and shows basically how we go from vacuum tubes to transistors and microprocessors, and it's kind of fascinating just to see that basically the entire story of computing from 1940 and on is about things getting smaller until we walk around with computers in our pockets that constantly transmit our locations every day. So miniaturization was the key, able to get personal computers at home eventually. Then the internet, global networked computers, the World Wide Web, which is an application that runs on the internet, which is basically revolutionized the world. The web is so large that companies have search engines and provide people with search engines to find content on the internet. The big themes these days are miniaturization and scale. In other words, things get smaller and there's a lot of them. We're talking about billions of users each accessing something. So how do you become a good programmer? I am of the firm belief that anybody can program, and anybody can learn to program. There's sometimes discussion like students are not cut out for programming. And I just think it's more of a work ethic thing than anything else, or just maybe it doesn't click the first time around, or there's other stuff going on in life. I firmly believe that anybody can learn to program. But here's the key. Being clever or having a knack only gets you so far. What really gets you to be a programmer is practicing. And that's why we give you all these homeworks. The idea here is that it's two keys. First is practicing, learning these keys, learning how to do things, trying new problems. The other thing is getting into a very paradoxically lazy mindset, which is that basically if I do more work now, if I do 4 hours of work now to automate this 1 hour task, I'm never going to have to do this 1 hour task again. And that's kind of the key to being a good computer scientist. We're very lazy we're very preemptively lazy, right? We work so that we can be lazy later. All right, so now with that, since we still have some time left, I might as well show you the very first program that we're going to write. So first off, what your lab is for this week is basically making sure that you can get Python working on your computer. So if you've had that lab already, you'll have seen that. And just basically doing Hello World. So to go and get Python, you just simply go to python.org. If you've got a Mac, you may have it already installed on your computer, and you just simply go over here and click this, and it will redirect you to the appropriate download. I'm running a different operating system. I'm not running Windows, so I can't show you how to install in Windows, but it will automatically detect what operating system you have and what you need. So you just download it, install it, and it will come packaged with a program called idle. So idle is now Python is named after, believe it or not, Monty Python. So Eric Idle being one of the creators of Monty Python, I believe. So that's why you've got a programming editor called idle. That's why you've got a lot of variables that will be named spam and eggs Python takes a lot of, there's a lot of humor in Python, and it's a very easy language to learn. So let's see, is anything being cut off there? No. Can everybody in the back see the code editor? Right? Okay, cool. I typically try to keep my size pretty large. So the first thing you do when you boot up Python or idle is that you get what we call a REPL, which is REPL, which stands for read, evaluate, print, loop. In other words, it's going to read what I type, such as 2 + 2, evaluate it, print it, and loop. Do it again and again, right? So as you can see here, I have a very boring calculator. Okay, so now there are two general types of languages. You have compiled languages and interpreted languages. Compiled languages are those that are like Java and C, where basically I write a program all in one go. I write this program, and then I tell the computer to compile it. In other words, translate it into translate the entire program into instructions so that the computer can understand, and then it will run it, right? The advantage of this is that basically this kind of thing, this compilation process is once it finishes, it's extremely fast and works the resulting program's extremely fast and works extremely well. Python, on the other hand, is an interpreted language, where what it will do is that it will look at one line of code at a time and translate it. Now, the advantage of this approach is that it allows the design languages actually to be a lot more flexible and a lot easier to work with. The disadvantage is slightly slower. You can think of that basically, the textbook makes this comparison. A compiled language is like, what if you translated an entire, basically what we do is that we translate an entire book all at once and then read through the translation, right? And then your computer will read that translation. In interpreted language, on the other hand, we're essentially just translating one page of the book at a time and then reading that page and then go translating the other page, right? So Python's what we call this interpreted language, and what you have to install on your computer in order for it to understand Python commands is the program called the Python interpreter. And that's what I've got booted up over here, right? Saying the Python interpreter, it's running off the GNU C compiler on Linux, which is my operating system. And so what it will do is it will take one thing, it will read one line at a time. But most of the time we don't program this. This is normally used to just show off, to like test little things and to run things. What we do is that we write scripts. Think of your computer as an actor, and what you're writing is a Python script. Directions for this actor to follow. So let's write the most basic program there is, which is hello world, which is just simply getting the program to print out hello, or the computer print out hello. Now first I'm going to show you what it looks like in Java, which is a different programming language. Public class hello. Let's see, public static void main string brackets args, another curly brace there, system.out.println. Don't type any of this down. Don't write any of this down. It's worthless right now. I'm just trying to show you. Now, if I was teaching 1068 like we usually did in our curriculum, I'd have to say, what is this? This is Blackmagic. Make sure this name matches the name on your file. What is this? Public stack void main. It's just Blackmagic. You're just going to have to memorize it for right now. And this is the line that prints out hello. That's Java. There's a lot of stuff that I just have to wave away as Blackmagic until like 3/4 of the way through the semester before you understand it all. I hate that. On the other hand, Python, if I just want to write a program that will print out hello, I just simply say print hello, because it's an interpreted language, and it will just execute one line at a time. So to run a program, I just simply say run, and there we go, run hello. That's your first program. Specifically, let's do hello world, exclamation point, because that's the way we do it. And then we run it, and then it will execute the script over here, and it will run this hello.py. Right? This is just simply saying it's in my home folder. It's in Andrew's home folder. Right? So print hello world. So first off, print, it's very important that it's lowercase. This will not work. Python and Java and C and all the other languages are what we call case sensitive, meaning that capitalization matters. Here, if I try to do it in shouty face, right, then it will say that it's it's not going to work. It doesn't identify it. So all lowercase, right? Next, it has these parentheses, which simply means it's a function. What's a function? A function is a command, built-in command in the programming language. So this is the print function, right? Be a bit inconvenient if you had to figure out how to get the bloody thing to print in the first place before we could actually print something out. So most programming languages have a bunch of functions built in, like print and adding things, because otherwise it'd be a bit tricky. Specifically, what we're printing out here is a string, right? And that's what's in these quotation marks. The quotation marks denote something called a string. A string is just basically text. It's any kind of text, actually, because Python is what we call Unicode compliant, which means that it's more than happy to do any kind of text whatsoever. So let's switch to Japanese for a second. Input mode, hiragana. So konnichiwa, which is Japanese for good afternoon. Okay, and then we'll switch back to English. Right. Notice that it rendered without any problems. When I started programming in high school, this would have been a huge issue, and my computer would have basically thrown up its heads and went and cried in a corner. Modern programming languages do, in fact, acknowledge that people do speak languages other than English. So as a result, you can, print out, text in other languages if you need to, which is fantastic. Okay. So that exists. We're not going to see that again until we get back to learning more about Unicode. But for the most part, right, we can put whatever we want to in here. Hello. Let's do another print line. Print, how are you? Question mark. So this is, by the way, kind of, necessary to put a closing parenthesis over there to say that we're ending the print function, right? What are we printing out? It's the stuff between the parentheses. What am I printing out? A string. Because we can print out other things than besides strings. We can also print out numbers. There's different types of numbers, by the way. This is what we'll learn that basically there's a difference between 5, which is an integer, and 5.0, which is what we call a floating point number. But we can print all of these things out, run, and we'll notice, hello, how are you, 5 and 5.0. Notice that they all appeared on different lines. Right? A print command just simply prints something out and then goes on to the next line. Hello, how are you? 5, 5.0. And again, this is a script. It executes one line at a time. Let's see. I'm going to do something that I can't do for a second and crash the program just to show you what I mean. What I mean that it does run one line at a time. So hello, how are you, 5? And then I didn't explain why. I tried adding 5.0 and this thing over here. Actually, I'm going to say the string A. I'm adding 5.0 to the string A, saying, and then it prints out, hello, how are you, 5? And then I guess since it's red, that means it's bad, right? Good guess. So it says traceback, most recent call, file, this is the file, hello.py, that's where I'm programming right now, at line 4. Ooh, cool. So it tells me where I messed up. Isn't that fantastic? It says print, this is the line I messed up, print 5.0, and it says unsupported, okay, operand types, operands. So, right, if we remember about operators in algebra, right, you've got the plus sign, and then you have the plus sign, the operator works on two operands, right? So unsupported operand types, or float and strings. So I guess that means you can't add a number and a word together. Kind of makes sense, right? Okay, so, but notice that with this, what it did is that basically, with Python, what it will try to do is that it will try to execute as many lines as it can, but as soon as it gets to an error, it just stops, right? This is a big difference. So you'll see that a lot. Basically, it's going to run one line, run another, until it finds an error. And once it finds an error, it's not going to run. Okay. So, any questions so far on the print statements? Yes.
So you said that after it finds an error, it's not going to stop printing. So, like, if I put something after that error,
yep.
It's going to run that line.
Excellent question. So I'll put in this should work, right? And what he asked was, So if it stops there, does that mean if I put something else after this line, like this should work? Will it not print it out? And the answer is no, it's not going to print it out. It's going to do the first 3 lines, right? Then it stops, right? Because we got into a faulty state and we don't know what kind of unintended, we don't want like any unintended consequences, like, you know, printing stuff over like stuff in memory. You know, if we got to a faulty state, we don't want to stay there. We want to stop what we're doing, right? It's like spilling dangerous chemicals in the lab. Don't, you know, just everybody move out of the way, don't, and stop what you're doing. So, so let's talk more about strings, because your lab for this week is fairly straightforward. We're asking you to do a fairly basic task, which is to kind of do a pseudo hello world. We want you to print out the biography of a famous computer scientist, right? And by short and it's a short biography, so we're saying 3 sentences long, right? So that's fairly straightforward. And to do some of what we call ASCII art, which means to draw something using, you know, using these, you know, these print statements. So let's talk more about strings. Now, notice that basically because we're using quotation marks to say what a string is, a string again being just a chunk of text put together, that if I want to say Professor, whoops, sorry, need that, Professor Rosen, or is it Professor Rosen said hello, period. Notice that we kind of get into a weird state over here, right? Professor Rosen said hello, right? Normally when you read some kind of document you get into this. But we get into an issue because quotation marks are used to denote the beginning and ending of a string. Professor Rosen said, and then we get to an end of a string, and then we have hello. And notice that's black. That means that Python's kind of looking at this as though it's a variable. What are variables? We'll get into them later, but they're like variables in mathematics, right? And so this just looks, and then it says, okay, we're going to start a new string here, parentheses. And now I can't run it because it's going to tell me I can't run it at all because the syntax is invalid. In fact, it's saying that basically that you have this program here and you didn't end it. And this, again, why are we getting this error? Because this quotation mark says end a string over here and begin a string. So we're kind of in a bit of a issue if we want to literally print out the character quotation mark. Because the character quotation mark has a special meaning, right? It has a special meaning there. So the way we get around that in programming is that we use something called an escape sequence, which is this / key, which says, I want to literally print out the character, the quotation character. So if I put in a / that says to Python, listen here. The next character that's coming is special. So now if I run it, it'll print out, Professor Rosen said, hello. Right? So escape sequences are basically used to print things that you could not normally print, like quotation marks. You also need to, or say a /, like print. Although Python 3 is kind of the weird exception, right? This will print a single /, as we'll learn, because we're escaping an escape sequence. We don't generally use, but what we generally use it for is something called, it is the new line. So remember, this is used for a bunch of interesting things. So we can use /t over here to introduce a tab between in our text. So /t is interpreted as being a tab. Professor Rosen said hello. And what if you wanted to make it make so you had more new lines? Well, we had the /n, which says in this character represents I want it to be on the next line. So the most important thing to remember about the escape sequences is that you've got, I'll write them on the board for you guys. You've got // to print out, which will print out a slash, a single /, /quotation mark, which will print out a single quotation mark, /n, which is a new line, which is useful because you can't really hit the enter key, right? And then /T, which is if you want to do a tab. And these are will be useful for doing your first homeworks. I've already posted the second weeks, by the way, in case you want to get started with that. But that is basically enough to get you started on your first lab. Now, when we come back here on Thursday, we'll actually start looking at the whole concept of programming and like getting started with actual programming. But this class was mainly introduction, some history, and introducing you to the print statement. Your job this week is to get Python installed on your computer at home. The lab computers all here have Python if you need it. But basically on the place you're mainly going to be working, get Python installed. All right, if you have questions or you have comments, concerns, complaints, please come to me.